high performing envelopes, but that's probably about 25% of the projects. The main use of the modeling software back in the day, I'll say, is we were proving lead compliance or lead points. And usually the model would be the last thought of the project. We design a whole project and we would say, okay, how many points do we get? We didn't take into account anything from the beginning of the project. So around 2014 is when we really transitioned to advanced, I call advanced early energy modeling, specifically with the IES tool, which is what I'm going to talk about today. We used advanced modeling early on in the process, not only to look at building envelopes and different architectural features, but advanced mechanical and HVAC features as well. So over the years, we're using this advanced modeling, we've collected a lot of data. So one thing with IES is it's user-friendly, it's customized HVAC systems, customized architectural systems, and over the years, you could build a real database with these systems. And with that database, what we've been able to do is increase the scale of our modeling. So not only are we looking at individual buildings early on in the design process, but we could build campus-wide systems, what we call a digital twin. So we've built campus-wide systems to look at transitioning to net zero, reducing overall peak loads, just overall master planning for facilities and campuses across the country. It also helps you plan your AIA 2030, which I know this is a goal of the group here. So building at scale and building your data with the modeling, the more and more you use it, the more data you have, and the more you can increase the scale of your projections. And then moving forward into 2021 in the future, what this data is really going to be used for in the future is real-time performance monitoring. So your building automation system is going to be tied into your energy model, and you'll be able to real-time track if the building is meeting what your energy model is projected. And that's going to be the next level of informing facility operations to really realize the savings that were projected. If you're investing in high-performance envelopes or high-performance HVAC systems, you want your investment to pay back. You really want to see the cost benefits. So that's where the modeling is moving in the future. But for the topic today, I was asked to look at some early questions specifically for envelopes. And this was drilled into us a lot already, but a couple of the key questions I came up with is the same as everybody else. Where is the building located? What is the building type? And does the investment in the building envelope really have a meaningful impact? So where's the building located? Is the site limited? Can you really do massing studies? Is it in a cold climate? Or is it warm climate? That really affects what we're looking at for the envelope. What is the building type? Is it an office building where it's less load intensive? Is it a research building where it's really load intensive? That also impacts your analysis. So what I'm going to attempt to do, I'm showing two different examples that have two different goals in mind. One is a commercial office building, new construction locally in the Philadelphia area, and the goal was code compliance. And then I'm going to look at major renovation to an existing building, higher internal load academic research building in cold climate in Ann Arbor, Michigan, and the goal was a more advanced sustainability approach to LEED Gold. So again, the tool that I used was IES, virtual environment. Some might consider it a pretty advanced tool because of what you're looking at the bottom right-hand corner, is the customized HVAC systems. That's the main reason Ballinger engineers really like using this system, is because we do a lot of high-performance HVAC modeling. But as far as architects willing to invest in the IES software, there's custom systems already made, and it's easy to assign an HVAC system early on in the process just for envelope studies. So when I'm building a model, I really try to do big block loads to speed up the simulation. So this is an example of an office floor. I broke the building into maybe 10 to 15 different zones. Each exterior zone Each corner office will get its own zone, and then the interior core will get its own zone. It really simplifies the model for early energy modeling. The speed of simulation. It just gets what you're looking for in the early concepts. You could also look at different load profiles and occupancy profiles for different people, equipment, lighting loads. It's really user friendly and easy to understand.
And Mike, if I could just jump in with two kind of quick points on this from the architectural side. I know we presented a number of tools in these sessions. And one thing I think that's true about the workflow here is you build a simplified model in IES. I know that's common to a lot of these programs. Sometimes you can import geometries, but often there's problems with the geometries as we've talked about. Yes, Brian, I think those are fins, but so we'll take a look. And then the other thing I'll mention is don't be intimidated by this kind of schematic mechanical system design or diagram, because one of the things to remember is we're kind of using default mechanical systems in this early modeling. In this case, we have a good idea of what that final default system will be. But again, what we're going to be doing is sorting out what variables, architectural variables, affect the greatest change early in the process.
Okay. All right, so the first example is the commercial office building in Philadelphia area. It's in King of Prussia. It was on an existing site, so this is our building of focus, and the orientation is really limited to the site. So unfortunately, there's a big east and west exposures. So in the morning, the sun is glaring into the east offices, and in the afternoon, it's glaring into the west. So peak load is really impacted. Again, the goal was code compliance for this. So the base system is a code compliant package rooftop HVAC system. So it really shows the impact where energy savings is going to come from is the envelope. Another thing to point out, when this building was being designed, Pennsylvania updated their code to the IECC 2015, which is the ASHRAE 2013 code. Philadelphia recently went to ASHRAE 9.1 2016, which is the IEC 2018. But Pennsylvania, outside of Philadelphia, it goes through the 2013 code. And what ASHRAE really looks at, every 3 years, the goal is to reduce the EUI target by about 5%. So Philadelphia really made a jump from 2007 to 2016. So they jumped almost 10 years. There's a 20% reduction in EUI, 15%, something like that. But it's a big reduction that we have to get our clients to realize what does it really take to meet code. So the key question for this study was, how do we optimize the daylighting in the building while saving energy? One of the main goals for this project was value space. So increasing visible light into your space. There are studies that show the more light that goes into your building, the better the occupants perform. Typically, an engineer would say, build a concrete block. That's how you save energy, but that's not really what invites people to buildings at all. So the goal was to increase the glass percentage to 70% for the building. So we broke down the envelope study into 4 different envelope analyses, where the first was a 40% glass building that met code, and that was the base point. So the EUI was about 57.6, and that was where the baseline is where we start our comparisons with. So with the 70% glass goal in mind, we then provided a low E glazing, and that met code. So what we showed is with a 70% glass and a high performing glazing, we can meet code with 70%, which is pretty impressive. And then we looked at adding exterior shading and horizontal louvers. The energy saving didn't really change that much. There was a 2 to 3% increase, or sorry, I should say reduction of energy. But the big savings that we realized with exterior shading is the reduction in the peak cooling load. So you see on the bottom right, the baseline system is about 100 tons. with exterior shading, your peak cooling load goes from 98 to 64, which is a reduction 40%. And what that means, it translates to your HVAC equipment cost reduction as well. So when you're looking at a code compliant system with which budget comes into play, and you're looking at a high performing envelope, which costs money, you have to point out, well, there's reductions in your MEP load and reductions in your MEP system cost that goes along with that.
So Mike, I just want to give you like a 5-minute warning so we have some time for questions.
I better speed up that. So a benefit of an IES model or an early energy model is you have the model built. You're not rushing through trying to build a model to prove lead compliance at the end. So what we've used the modeling tools as well, since you have it built already, you can use it during the CA phase. For this specific example, I won't get into the numbers here, but the curtain wall that we proposed, the 70% curtain wall, was a little bit over budget, and we were looking at different options to that met the same performance with the first cost in mind. So even though a bunch of the curtain walls had close to the same performance, because we were so close to meeting the new code compliance, there was a few that were really, really close to meeting code. Even, of course, those are the lowest first cost. We could use the model to do more than just look at the early energy savings. It could be used throughout the whole process and whole project. So just to close out project sample number 1, the energy model generates useful data beyond your net zero assessments, and it can be used throughout the whole project. So we look at ways to maximize daylighting in the building, reduce your peak load, and capital spending assistance. Point out the site orientation limitations can increase the burden of the envelope, and low internal equipment loads and code minimum HVAC systems really heighten the importance of the building envelope. So I wanted to show 2 examples because I thought this was pretty interesting. An existing academic research was with higher internal loads. I want to show the benefits of early energy modeling that could show the envelope still has importance in your design. So this was in Ann Arbor, Michigan, which was a cold climate. It was a 100-year-old building. So the glass was replaced in the 1980s, but the facade stayed for over 100 years. I'd say about 50% of the building was lab and 50% was classroom. The goal of the project was a 50-year transformation, which means they did have money to invest and they wanted to have a quality investment over time. So the key question here was, does the envelope investment have a meaningful impact? It costs a lot of money to update your building envelope. And for this building, you're looking at the glass, it's about 60% glass for the building. So this is when we really implemented the IES energy modeling during concept design to see where your actual load was being projected to be used in this building. And what we saw was, in a cold climate in a research lab, your heating dominant. 54% of the load was heating. I would say half of that was due to the ventilation air required to meet your lab minimum air changes, but half of it was directly due to the envelope. You see here the envelope on the building in every aspect, from wall U value, window U value, shading coefficient, and most importantly, the infiltration rate through the window frames is drastically lower than code. So you could have a high internal load building with a low performing envelope, and the low performing envelope really does impact your energy saving, your energy usage, I should say. But the key question that should be asked is, what is the engineer missing? Because when I saw that load 54% heating, I originally thought add insulation and you're done. That's good. That's all you need. But the architectural team did the condensation analysis, and what they really found was, with the 100-year-old facade, if you add insulation and a vapor barrier, what you're doing, you're increasing the freeze-thaw cycle inside of a wall by 10 times. So you have potential to damage the wall by installing insulation and the vapor barrier. So we really had to come up with an ideal solution on how to handle this building while saving energy. So I'll try to get through this pretty quickly. We installed an HVAC system that had heat recovery to meet the ventilation load reduction, which was significant, it was 27%. But for the envelope, we needed to get to a higher percentage to meet LEED goal. I would say the goal was 30% energy savings. So for the envelope study, we assessed 3 different scenarios. We broke out the envelope to add insulation and the air vapor barrier. Option number 2 was to seal the window frames where significant infiltration was being noticed. Option number 3 was to replace the existing glazing. What we did with all 3 of these options was really we tried to have first cost in mind. But since the glass was low performing and the leakage to the frame was so significant, we tried to combine both of those into proposed option number 4. And you really saw through the modeling process a huge peak load and reduction in heating because we knocked out two birds with one stone, the window and the frame. Even though the energy, the cost of the system was way higher, but 2, the energy savings and the reduction in the HVAC system cost really made that option noteworthy. So the last thing is, the key question is, can actual design, architectural design, be enhanced through envelope and HVAC interconnection? So again, the peak load is really reduced by a high performing envelope. And what it does is it reduces your HVAC system first cost, your air handling units, boilers, chillers, ductwork, piping, all goes down in size. And it really opens up your building to more architectural appeal. You could have higher ceilings, more innovative design solutions, and smaller mechanical rooms and smaller penthouses. So that's the takeaway. Even if your building is internal load driven, given the climate and existing facade conditions, your envelope really still plays an impactful role in your building energy usage. And if we really combine architectural and engineering interactions together, you can come up with an ideal building design that incorporates smaller HVAC systems and more valuable spaces. So with that, I have 1 minute, 43 seconds left.
So we do have a question. Fortunately, people have been queuing them up. So there's a question: do we use IES for our LEED model documentation? Do you want to just talk about that for a second?
Yes, we definitely. IES has a template to actually submit to LEED. It's a really user-friendly navigator that goes step by step into the modeling process to outline LEED requirements, and then there's an output that can be uploaded directly to LEED. So it really fine-tunes the LEED process.
Mm-hmm. As I mentioned earlier, we've on the architectural side, our mechanical team is a lot more comfortable, assessing projects early because they have these default mechanical systems, built into the model for evaluating options. There was another question. Okay, actually, I think that was may have been from the previous talk. But I did want to just kind of, emphasize, one of the surprising things about this Michigan project is, well, maybe not so surprising, is you look at the amount of glazing. It actually wasn't that significant to add insulation to the opaque wall systems. What was most important was to fix the windows. And that, not a very sophisticated solution maybe, but that was actually, at the end of the day, we could demonstrate through this modeling process what an impact the windows and, as Mike said, the frames had in reducing that peak load. And I see we're ending, so I think we're, I don't know if we're going to be kicked out or not. It looks like they've been giving us another 2 minutes perhaps. So yes, I think, sometimes these models can validate, our hunches, but other times I think they can surprise us. So we do have probably a few seconds if there's any other questions before we exit. Okay. Well, Mike, thank you very much. That was a great run through. Unfortunately, I was late in starting to record it, but I got most of it. So You might recognize Brian Smiley there.
Yeah. Hey, Mike. Good to see you. Thanks. Great job. Good stuff.
Sorry I had to rush through it at the end.
No, that's okay. It's hard to gauge how long you want to talk about these things.
Lots of great information to get to us, and it came through really well.
Thank you. Thank you.
Sherman loves windows. Yes,
Well,
not big
I think-
ones, the right sized ones.
The right size, yeah. If we have a second, one question was for the new office building. It looked like the 70% glass was okay because it benefited daylighting inside the office. And you had used a better quality glass? Is
Yeah.
that-
We overcame the quantity of glass by having a higher performing glass than code.
And the
Okay.
fins too. You know, the fins reduced some of the heat gain on the envelope as well.
What were the fins?
Agnostic to mechanical systems. So you're able to really isolate and look at the impact that certain envelope choices, decisions have on the internal heating and cooling loads. So one of the things that Al made the point of is that it's a bit of a misnomer of this being passive house. You can utilize this tool for other project types. It can do not just residential, but commercial, non-residential as well. And within this particular test that Al had set up, we were seeing that, you know, the three biggest areas of impact was windows, walls, and ventilation. And with pretty ease of just changing some values in the window performance and the wall performance, was able to do iterative order of magnitude, where you could sort of see the order of magnitude impact that making you know, a higher R value had on the heating side. This is based in Philadelphia, similar to, you know, the heating and cooling loads that Al's used to in Chicago, but could see that as the heating loads were being decreased by the choices on increasing performance of the wall and the windows, that it had a subsequent impact on slightly, but only slightly higher cooling loads. But the nice thing about it was that the load piece of this was the peak loads. You could see how that peak load could have a positive impact on the sizing of equipment once our engineers, you know, come into the equation to start sizing things accordingly. Did I miss anything now?
No, that was a very generous summary. Thank you. Yeah, and like I had mentioned too, like as architects, you know, you are in control of everything that happens with the enclosure and the enclosure detailing. So that's your chance to make the biggest impact on space conditioning loads, which is half the energy used in buildings, and buildings make up 40% of the energy used in the country. So I think there's a good case for that.
Thank you, David. Thank you, Al. Lauren or anyone else? Go ahead. I guess one of the takeaways from our group, the Ladybug Tools sessions, I think we really focused on process to kind of look at how we can be doing these studies to build on each other. So, you know, studying a building with all glass versus a building that is kind of a refrigerator, and then taking the order of magnitude understanding of which one uses how much more energy to then influence it with your architectural perspective to say, okay, well, if my all glass facade is going to be the worst, like where do I want to place that glass optimally? And if there's an architectural reason to not put it in an optimal location, what are the loads that I need to be concerned about in order to maybe shade that glazing from different perspectives, and just kind of building up a process of using some of that analysis. And we also talked about maybe the analysis isn't necessarily trying to solve a problem, but it's trying to identify the problem. So that's kind of like the broader discussion that we had about process and concept using the design examples.
I think we talked about kind of similar concepts of, isolating elements, looking at those individually and what impacts they might have on the overall success of the energy model, and then starting to group those together as kind of bundles of options to start to create your final or your, best case scenario for that project.
Okay. Are there any questions for any of the presenters, me, before we kind of, okay. I'm really glad we're doing good on time today. So let me go to the next slide. So
Well, we have Josh. Is Josh still on
Oh,
here to
yes,
talk about?
I am here. Sorry.
Oh, yeah, sorry.
We kind of ran over. We took advantage of our extra 120 seconds there. But
sorry, I didn't
yeah,
see you
no,
there.
that's okay. That's okay. I wasn't sure what you guys had talked about so far, but I think I heard some of the same themes. So Mike presented some analysis or some studies that we had done from project, but two kind of projects at different ends of the spectrum. A new office building, kind of a ubiquitous construction type, developer-driven project, and then an existing 100-year-old envelope, kind of an industrial aesthetic, 60% glazing, and how we use modeling, both kind of on the front end of evaluating a project that was really seeking to do better than code versus a project that was seeking to reduce its, to beat code by 50%, kind of, again, two ends of the spectrum. And I think, one of the things that was particularly interesting on, so the office building was trying to seek to get to 70% glazing to maximize daylighting. The owner was pursuing well certification, and through manipulations to the envelope and shading and glazing performance, we were able to model how that could incrementally improve. And then with the university building, with the research lab, it actually turned out to be not favorable to add insulation to the walls. Really, the real energy liability was the windows and the frames themselves that were responsible for the most infiltration and exfiltration from the building. So that was where the project team targeted its resources, and that allowed the systems to get smaller, and that allowed the ductwork to get smaller, the ceiling heights to get higher, et cetera, all the things that we love as architects. So,
That sounds awesome. And I'm sure the client was really, really happy to not spend money on insulation and spend that money where it needed to go. That's the power of these tools, is like being able to back your decisions or your instinct with like real numbers and real action that folks can really relate to. Awesome. I want to, before we go into takeaways, I want to thank all of the presenters. Thank you so much for sharing what you guys are doing at your firms and using the different tools. I think this is the kind of dialogue that we need to have, more frequently across the industry. Like, what are you guys working on? How are you doing it? Let's learn from each other, because technology moves way too fast. It moves faster than we can keep up. And anyone who uses Ladybug tools probably knows this, right? Like, there's a new version out, and then all of a sudden you're like, how can I do this? But anyway, looking at kind of like takeaways for what you might want to walk away from this presentation on is, I'm going to flip that question or the statement from Freakonomics. So knowing what to model and how to model it makes a complicated design problem much less so. And energy modeling isn't useful if you're just attacking the noisy part of the problem that happens to capture your attention, or if you are thinking of only the parts within that, right? So there's a lot of emphasis. We had a conversation with Kim Shin, who joined us in August, where he talked about an architect who came to him and said, I want to maximize spatial daylight autonomy in my building, and that's going to get my energy to be where it needs to be. And, you know, Kim Shin looks at him like, what are you talking about? Like, there's all these other factors that contribute to energy. So, you know, not just focusing on what seems like the cool thing to do. And we want to focus on loads. This is actually, I should probably put that one first. Like, focus on loads, not EUI in early concept design. EUI is always going to be there, and it's still a very good metric for comparing buildings, but that's what it's useful for. It's useful for comparing one building to another building. It's not useful in design, right? Like, we just, yes, net zero buildings, we need to reduce our EUI. But when we're thinking about it in the design process, we have to move away from EUI. And then we have to think like an architect and an engineer. And the series that we're going to do at the end of this year is going to be about this larger topic. So I'm going to kind of leave it at that and kind of talk about our next monthly meeting, our AIA Philadelphia meeting. We meet every Thursday. There's a link and it will be shared in the slides. And we welcome new members if you're not a member right now. And we have a couple of subcommittees that we are always looking for new voices and new opinions for. The 2030 commitment meets on Mondays. And now that I'm looking at this, we should have a link to our Philly calendar in here so that folks can subscribe to it and join us in these conversations. I think that's the last slide, yeah. All right. Bunny, David, anything you want to add?
We're getting lots of great feedback on this, and thank you all for coming to join us, and Janki and Josh for organizing this great panel of presenters for this. Yeah, we're, as Bunny says, we're a band of leaders. We're yes people. So all these subcommittees, some of these didn't even exist over a year ago. We're always open to new people coming and participating in our group. There might be more subcommittees that we don't even envision today, that if you show up tomorrow and you're like, this is something I'm really passionate about, then the more the merrier. This one is obviously born out of our 2030 commitment. So as Josh said earlier, it's really, I mean, this is one of the two critical things that AIA National is focused on, is the charge for carbon neutrality. And we all have our part to play in this. And it's not necessarily about meeting the 2030 carbon neutrality. That's where we want to be, but we want to be striving towards it. We want people to sort of know how they're doing today so they can figure out how to be better tomorrow on this. So we just, you know, we had to start with each incremental step along the way. And it is really easy to start this. So we encourage anyone who's not currently a signatory to the 2030 commitment. Is really easy. They even give you the boilerplate letter to sign up for this. And you know, you probably have your fingertips on the information about how you're doing, or you can easily get to that information. And you know, that's how we understand how we can improve, by understanding where we are on that. But this is just one of many: policy and advocacy, environmental justice that we started last summer, zero waste that we started over a year ago, and design awards. We have a lot of really great people participating in COAT, and we welcome you to join us.
Thanks, everyone.